This is 5.2, Solving Systems of Linear Equations by Substitution, Part 2. So just to remind you, to solve by substitution we have a few steps. First, you're going to solve for one variable and plug it into the other equation. So, you could solve for y. So you get a y equals and a bunch of stuff. Take that and plug it into the other equation. Then you're going to solve for the other variable. So you take your y equals, plug it into the other equation, then you're going to solve for x. Then you get an x equals a number, plug that into an original equation, and get the remaining. So you take x, plug it in to get y. You're going to get an x number and a y number. Those go together in an ordered pair. So we are going to take x plus y equals negative 2, and negative 3x plus y equals 6. So, first thing, solve for one variable. So I'm going to solve equation 1 for y. To do that, you subtract x on each side, so you get y equals negative x minus 2. Take this, plug it into your other equation. So then you have negative 3x plus y, but y we said was negative x minus 2 equals 6. Negative 3x minus another 1x is negative 4x minus 2 equals 6. Solve for x, and you get x equals negative 2. Then you take your x number and plug it in to an original, and you're going to solve for y. So if I plug it into equation 1, I get x plus y equals negative 2. Solve for y, and y equals 0. So you put your x value and your y value together, and you get an x, y coordinate. Let's do another example. X minus 2y equals 7, and 3x minus 2y equals 3. I'm going to take equation 1 and solve for x. To do that, you add 2y to each side, so x equals 2y plus 7. I will plug this into where x is in equation 2. So I have 3 times 2y plus 7 minus 2y equals 3. Now I'm going to solve for y. So I have 6y and a minus 2y to make 4y, plus 21 equals 3. Solving for y equals negative 18 over 4, which reduces to negative 9 over 2. Now I take my y value and plug it in for y into one of my originals. So if I have negative 2 times negative 9 over 2, that reduces to positive 9. Solving for x equals negative 2. So my point is negative 2, negative 9 over 2. Now in this equation, it's a little bit different, and it turns out to be a little bit special. So if I have 2x plus y equals 5, and 4x plus 2y equals 10, I'm going to take equation 1 and solve for y. That means subtracting 2x on each side, and y equals 2x plus 5. Take that and plug it into your equation. And after you reduce that a little bit, I have 4x minus 4x plus 10 equals 10. So 4x minus 4x is 0. So then I just have 10 equals 10. And if I look back at my original equations, equation 2 is the same as equation 1, just multiplied by 2. So I have no variables left, which means I have infinitely many solutions. It does not matter what x and y are, because they'll be gone when I solve for them. If I were to solve this by graphing, these would end up being the graphs of the same line. So they are going to be graphs on top of each other, and so they have every point in common. So we say infinite solutions. Now in this equation, I have 1/2 x plus 3y equals 12 and 1/2 x plus y equals 6. These both have a 1/2 x. So when you have two equations that have the same term, meaning these both have a 1/2 x, you can solve for that term and then substitute. So you can solve for a term instead of solving for just x or just y. So if I solve equation 2 for 1/2 x, I subtract y on each side, and I get 1/2 x equals negative y plus 6. Then I'm going to take this and plug it into equation 1 and solve for y. So plugging it in and reducing, I have negative y plus 3y is 2y, plus 6 equals 12. Solving for y equals 3. So take my y equals, plug it into an original. So I'm going to plug it into equation 2 and solve for x. So then I have 1/2 x plus 3 equals 6. When I divide by a fraction, I have to multiply by the reciprocal, and I get x equals 6. So my point is 6, 3.